After studying this module, dear students, you shall be able to know that Wittig reaction is one of the best way to prepare alkene, where the double bond you require at a very particular specified position. You shall be able to learn about phosphonium elites, how they are formed and about their stability. You shall be able to learn about the mechanism of Wittig reaction, and you shall be able to analyze the steric hindrance factors which are involved in the same to predict which particular product will be formed as a major one. So, let us begin by going into some introduction. So, let us begin with knowing a new term which is elides. Compounds having adjacently placed covalently bonded atoms bearing opposite charges and with complete octets, they are called as elides. The elides can be at nitrogen, sulfur, phosphorus, but when we talk about phosphonium elides, they have phosphorus bearing the positive charge which is covalently attached to carbon, which in turn is having a negative charge. And these phosphonium elides, they can be represented by the structure as you can see here, where there is a double bond between the phosphorus and carbon, and alternatively you can see it is the phosphorus which is plus and carbon which is minus, and they are adjacently placed, and that is why this is an elide. When a phosphonium elide is reacted with an aldehyde or a ketone, as a result of this combination alkenes are formed, and this reaction is called as Wittig reaction. The reaction is named after George Wittig, a German chemist whose studies in organic phosphorus compounds won him a shared Nobel Prize in chemistry in 1979 along with H.C. Brown. So, with this background, let us study the Wittig reaction in detail. In Wittig reaction, as I told you, an aldehyde or a ketone is reacted with phosphonium elide, and as a result alkenes are formed. So, if we try to understand the reaction with the help of a general reaction, this is how it can be represented. First of all, you can see how the triphenyl phosphine with this halide can be used to prepare this phosphonium salt, and in the presence of base there can be removal of this H and Br, and as a result there will be formation of this particular elide which is the Wittig reagent. So, you can see here this elide which is represented here, the PH3P plus with C having minus joined to R and R1. And now this particular Wittig reagent or the phosphonium elide, when it is reacted with any aldehyde or ketone, you get the alkene which is represented here. And very important thing here is that there is no rearrangement. The double bond of alkene which is resulting as the product is formed at just the same position where the carbonyl double bond in the aldehydes or ketones were there, and it will be joining to the very same carbon of the phosphonium elide which is bearing the minus charge. Let us look at these examples. Here you can see in this particular case acetone when reacts with this particular phosphonium elide will be giving you this particular alkene, and the triphenyl phosphine oxide is the byproduct. Similarly, you can look at this particular cyclic ketone cyclohexanone reacting with this particular phosphonium elide, and you get the double bond at this exocyclic position. And otherwise, if you recall, the exocyclic double bonds are very difficult to prepare, because any other route if you take, you will end up with more stable endocyclic double bonds. So, notice here there is interchange of the doubly bonded carbon part of the elide with the carbonyl oxygen, and the trialkyl or the triaryl phosphine oxide is the byproduct. In order to understand the mechanism of this reaction, let us first know more about the Phosmonium Elite, which is also known as the Wittig reagent. Phosphorus atoms, especially those that are positively charged and are attached to electronegative substituents, can increase the acidity of protons adjacent to them at the carbon skeleton. Deprotonation by a moderately strong base gives rise to a species which is called as phosphorus elite, and this carries a double bonded species called phosphoranes. The phosphonium elite required for a specific synthesis is produced by an SN2 reaction of triphenyl phosphine and an alkyl halide with the suitable number of carbon atoms as you require for preparing a particular alkene. So, as you can see in this particular equation, R3P with this particular alkyl halide, first of all you get this intermediate salt, and then further reacting it with the appropriate base, there will be removal of H and X and we get this particular phosphorus elite or the Phosmonium elite. So, if we take one particular example starting with this cyclopentyl bromide and then followed by treatment with base, you can see this particular proton will be taken out from the phosphonium salt, and the appropriate base which is butyl lithium here, you get this particular elide, and this elide you can see it can be equivalently represented by this alternative representation where there is a double bond between the carbon and phosphorus. So, this is the phosphorane and this is the elide representation. The elides are intensely colored resonance stabilized structures and it bears positive and negative charge on the adjacent atom. Elides are generally not surrounded by solution in which they are prepared. Therefore, they are generated in situ during the Wittig reaction. Let us also now try to understand what are the different types of elides. The elides are of two types. First, those with conjugating or anion stabilizing substituents adjacent to the negative charge such as carbonyl groups, and the other ones are those without any stabilizing group. The former, which are joined with conjugation or the anion stabilizing substituents, they are called as stabilized elides because the negative charge on the carbon is stabilized not only by the atom of phosphorus but also by the adjacent functional group via the enolate type of structures, and the later ones are not having such stabilization, which are referred to as unstabilized elides, as you can see here. After understanding how elides are prepared and what are their types, let us try to understand the mechanism of Wittig reaction, that is how it is actually taking place in various steps. The Wittig reaction converts the carbonyl CO double bond of an aldehyde or a ketone to a CC double bond using phosphonium elite. Elides are nucleophilic species which attack the carbonyl group of aldehydes or ketones, generating the four-membered ring as intermediates which are called as oxaphosphatanes. Oxaphosphatanes are unstable. They undergo elimination to form an alkene with phosphine oxide as a byproduct, as you can see here. The phosphorus oxygen double bond is extremely strong, and it is this that drives the whole reaction from the oxaphosphatane intermediate and resulting in these two products, one alkene and the other with the phosphine oxide. For the formation of oxaphosphatane, we can take this reasoning. The carbon bearing negative charge in the elide attacks on the electron deficient carbonyl carbon, and this results in the formation of a betaine as you can see here. So, this butane is not a completely cyclic set, it is in between, where the C minus has attacked on the carbon of carbonyl, and as a result there is a O minus, this alkoxide ion in this particular form, which is formed as you can see here, and this is what is called as a butane. And it is this further O minus and P plus will be joining, and that is where you will be getting the formation of this oxaphosphetane as the intermediate. So, the fact is the occurrence of butane has not been established, although we can understand it happening via this hypothetical butane. On the other hand, 31P NMR experiments, they have confirmed the occurrence of 4-membered oxaphosphetane intermediate. So, therefore, if we draw a conclusion from this fact, the initial step is believed to give the oxaphosphetane directly without the butane formation. This you have to keep in mind. But the mode of attack is same, that is the negatively charged carbon of halide attaching to the electron deficient carbon of the carbonyl, and the positive charged phosphorus of halide attaching itself to the oxygen of the carbonyl group. But this is happening simultaneously. So, there is directly the formation of oxaphosphetane intermediate and not butane. Note that the double bond of alkene is formed just where the carbonyl double bond was there in the carbonyl compound without any rearrangement, as I have told you earlier also. Hence, Wittig reaction provides an excellent way to prepare the alkenes, which by other methods are very difficult to prepare, like the terminal double bonds, exocyclic double bonds, etc. After knowing the mechanism, let us now try to understand how the steric hindrance factor affects in Wittig reaction. For alkene synthesis, if there are two alternative routes possible, then that route is preferred where the phosphorus halide reagent has less steric hindrance, that is less bulky group or less number of substituents. And this is because the preparation of less sterically hindered halide is convenient, as the preparation is an SN2 reaction, which you are already aware that it is favored on the less hindered alkyl halide. For example, for the synthesis of 3-ethyl 3-hexene, as you can see, these are the two possible routes. It is better to use a 3-carbon alkyl halide for halide formation and a 5-carbon carbonyl compound, which is depicted here by route 1, as compared to the other possibility, which is shown here as route 2, wherein a 5-carbon alkyl halide is used for halide formation and a 3-carbon carbonyl compound is used along with that to give the Wittig reaction. So, clearly out of these two, you can see this upper route is the preferred route that you can say for the formation of this particular alkene. Let us also now try to understand the stereochemical perspective of Wittig reaction. In the Wittig reaction, the intermediate oxaphosphetane is diastereomeric and it can be syn or anti. Formation of oxaphosphetane depends upon several conditions. Let us take them one by one. First of all, let us consider it with the unstabilized halides. In the Wittig reaction of unstabilized halides, Z alkenes are formed as the predominant product. The halide approaches to the carbonyl compound to form a 4-membered oxaphosphetane pucker ring in the intermediate state. The formation of transition state takes place in a way that the substituents larger in size kept away from each other and a syn oxaphosphetane is formed. This is unstable, but it forms at a faster rate than the anti-oxaphosphetane possibility. And this finally produces a kinetically controlled Z alkene, as you can see here, as the major product. Talking about what happens in terms of stereochemistry when you are using stabilized halides. In the Wittig reactions of stabilized halides, E-alkenes are formed. Let us try to understand how. Since the oxaphosphatane formation from starting material is reversible and halide is stable, an equilibrium is established between the less stable syn form and the more stable antiform of the oxaphosphatane, as you can see here. So, therefore, before the decomposition, the syn oxaphosphatane and the more stable antiform, they interconvert slowly, and hence it will give rise to the E-alkene. Thus, the selection of the E product, you can say here it is thermodynamically controlled, and this you can see here as shown. So, the E-alkene here is the major product in contrast to the Z, because of this equilibrium where it will come to more stable anti-oxaphosphatane, which will further give you the E-alkene as the major product. So, after understanding about Wittig reaction, let us look at some examples of the Wittig reaction. First example you can consider as shown here, cyclohexanone reacting with this particular halide, which in turn is prepared from triphenyl phosphine and CH3Br in the presence of appropriate base, where it is NaH is the base used, and this will combine and you get this particular exocyclic double bond. Another example is the exocyclic double bond formation on camphor by reaction of methyl triphenyl phosmonium bromide in the presence of potassium tertiary as the appropriate base, and this you can clearly see here. This particular carbonyl is getting, the carbonyl oxygen is getting replaced with the CH2, and this new double bond is formed at the same position where the carbonyl double bond was there. Another reaction you can see here is the reaction of propanol with butyl triphenyl phosphonium iodide, whereby at least stabilized halide selectively forms 3Z hept 3-ene. So, this is the stabilized halide and it will result in the formation of this particular Z alkene. And in another example you can clearly see there is a E-alkene formation when benzaldehyde reacts with this particular halide. Notice that it is a stabilized halide, and that is why it is now giving you the E as the major product. Let us now talk about the advantages of Wittig reaction. Wittig reaction boasts higher functional groups selectively, in which the carbonyl units can be very selectively transformed into alkenes at that very particular position. Another important advantage is that it involves very mild reaction conditions, such as its ability to proceed at low temperatures. Using an alternative olefination technique such as these E2 elimination requires strongly acidic or basic media, if you recall, along with high temperature, and yet these harsh conditions are accompanied with regioselectivity issues. In contrast, Wittig reaction is easy to control and often proceeds in high yields, and this is a strong favorite in organic synthesis to prepare double bond at the very specified position where you want them to be there. After knowing Wittig reaction, let us also try to know there is an improved version of Wittig reaction, and that is called as Horner-Wittig reaction. The primary disadvantage of the Wittig reaction includes the occasional difficulty of eliminating the phosphine oxide which is there as the side product. An improved reaction, which is called as the Wittig-Horner reaction, and it is also called as the Horner-Wadsworth-Emmons reaction. It employs phosphides in lieu of phosphines and thus produces a highly polar or water soluble phosphorus side product, and that can be easily removed. Often it is better not to use the phosphonium salts but a phosphonate instead. Sodium hydride or alkoxide anions may be used to deprotonate phosphonate esters to form enolate type anions. These anions react with aldehydes or ketones to form E-alkenes. Alkene forming reactions of aldehydes or ketones with phosphonates, they are called Horner-Wetzert-Emmons reactions. If we look at some examples, you can see this is the general representation of the phosphonate ester that you can take, and this reacted with the base, there will be formation of this oxyanion which is resonance stabilized and via this enolate. So, you can see it is highly resonance stabilized phosphonate ester. So, this will be acting as the elide then, and with this particular carbonyl compound it substituted cyclopentanone, and when this is reacted with this particular phosphonate ester in the presence of sodium hydride, then the combination of this molecule happens so that we get this particular alkene at this particular position. So, very similar to the Wittig, but this is a modification, and rather than phosphine, now we are using these phosphonate esters. So, let us now summarize what we have learnt in this module. We have learnt about Wittig reaction, and this is a reaction which transforms the carbonyl bond of aldehydes and ketones, that is the C double bond O gets converted into C double bond C, and the C double bond C of alkenes. And this is the method most often employed for synthesizing alkenes with defined substituent geometries. You can prepare E, you can prepare Z, as we have already discussed in detail. This involves the use of phosphorus elide, and if we talk about elides, these are the chemical species which have phosphorus bearing positive charge, and there is an adjacent carbon which bears the negative charge. The primary disadvantage of the Wittig reaction includes the occasional difficulty of eliminating the phosphine oxide side product, and this is overcome by the improved reaction which is Wittig-Horner reaction, and this employs phosphides in place of phosphines, and it produces highly polar or water soluble phosphorus side products that can be easily removed. And let me recap the stereochemistry part of Wittig reaction also, which is very important. The Wittig reaction stereoselectivity depends upon the structure of elide. The stabilized elides, they produce primary E isomers, and the unstabilized elides will give you Z isomers, as you can see in these two particular cases.